Let's talk for a moment about buckling. You guys did a little bit of instruction in buckling in ME 211. Does anybody remember what you did with buckling? What is buckling? Why are we concerned about buckling? Doesn't have to be a rigid definition. What is your impression, thoughts?
It can be a failure, and you don't want your design failing.
Okay, so it's a type of failure, right? The obvious type of failure is when something breaks into two pieces. There's other types of failures. One of those is buckling, which is a structural collapse. I think other one we've commonly talked about is just excessive deformations as being a failure. If a shaft bends so much the gears disengage, then that's a failure of that shaft. Okay, so specifically then, what is buckling?
It's usually like a vertical beam or some type of concrete.
It's compression.
Okay, right, it happens typically in compression. And in 211, we looked at different beam types, right? So think of like buckling of a building column or buckling of a piece of a truss structure, right? Okay. So in 211, I've got some material on all this in just a second, but in 211 we looked at something like a column that looks like this, that's attached to the floor, and we have a vertical load on it, and we called that P critical. And the question was, what can P be without that column buckling? Okay. So we'll talk about that a little bit. That's generally what buckling is. The reality, though, is that buckling happens in a lot of other cases rather than just that type of case. And so I can't remember what pictures I've showed to which classes, and so I put these up here. If you've seen these before, then you can admire them again or whatever. So have I shown these to you? No, you haven't seen these. Okay, good. All right. So this is this a failure? Yeah, I think this thing failed pretty badly, didn't it? And since we're talking about buckling, then I think it should be pretty obvious that this must be a buckling failure. Is that a vertical column with a load applied to it? No, clearly not. So here's an example of something that buckled, failed catastrophically in compression that is not a column with a load on top of it. So in 211, your only tool for determining if buckling is going to happen, what is the P critical, is going to be the J.B. Johnson or the other equations of buckling that applies to a column with a compressive load on it. Those equations are not going to be applied very readily to this particular circumstance. So, any guesses as to what happened to this train car? Here's another view of it, by the way.
Low pressure inside and crushed by atmosphere.
Okay, so it's a pressure problem. Specifically, so this was sent to me by a friend of mine from college a number of years ago. He worked for I can't remember the name of the place. It's on Newburgh Road, right at the Waterston Expressway. C&I Engineers, I think. C&I Engineering. If you're familiar with that area, there's a building there. You can see C&I Engineers or C&I Engineering or something like that. It's up on top of the building. It's a big, like 15-story building right at Newburgh Road and the Waterston Expressway over in Louisville. And they do a lot of piping and other engineering type of tanks and apparently something with rail cars and so forth at CNI Engineering. I'm not sure if he's even there anymore, but he sent me these pictures, and this was a case. So this is obviously a tank car for a railroad, and specifically what happened with this is that they were cleaning it, steam cleaning it, and when the employees went home for the day, they inadvertently closed the hatch on the top of the hot, steamy train car. Okay, so the interior of the tank was full of steam. They closed the hatch, which then sealed it. And then what happens, of course, with steam, it cools off and it condenses, right? So it created a vacuum inside of that tank car. And they showed up for work the next morning, and this is what's sitting there waiting for them. So can you imagine if you were the one that was cleaning this the day before and you show up for work the next morning and that's what's sitting there? Yeah. That would be, I don't know if they were terminated or not, but that would be rather upsetting. But that's simple physics. How much vacuum can that tank car take? Well, apparently not a whole heck of a lot, because the steam condensing inside of it, crushed it dramatically. Okay, so what I wanted to talk about today is using Solidworks to predict the likelihood of buckling under certain loads. So could you use the equations we used in 211 to predict that? Absolutely not, or at least not with any great deal of confidence and certainty. Can we use Solidworks to predict that? Well, actually we can. Okay, and so that's the point of our discussion today is Solidworks has a buckling analysis that we can use to predict the likelihood that a structure is going to buckle. Okay, so I have a little bit of information here. Here's a more rigid definition of buckling: the sudden conversion of axial strain energy to bending energy without a change in external loads. And the dramatic thing about buckling is that it happens suddenly and without a lot of warning. It's a catastrophic collapse. So it would have been really fun to have a video of this thing going. Probably it was sitting there, and 1 second it was completely intact, and the next second you heard this crashing noise, and then it shriveled up and sucked in on itself.
There is a video.
Okay. Hmm?
There is a video of something like that.
Yeah. Okay. Of a whole train car.
Yeah, exactly. Yeah.
Okay. Awesome. Well, then that'd be fun to watch.
Yeah, it's instantaneous.
Yeah. It just pop and it sucks it in. The same thing is fun when you're at a bonfire with your beer can, kind of. Well, I'm sorry, I'm sure you're drinking soda at the bonfire. So you take your soda can and you put a little bit of water in it, you put it in the bonfire, and you let it start boiling, which of course fills up the interior with steam. If you then take the can, turn it over, and drop it in a bucket of water, it'll do the same thing, and it'll crush the can, just like you stepped on it, type of thing. So just fun with physics of steam and condensation and so forth. The calculation of it, we're going to have a singular matrix. And so we have to do some elaborate things that are behind the scenes. That just be aware of the fact that there are multiple ways to do this using finite element analysis. You can use linear equations to predict this, and you can use nonlinear analysis. And we've not talked about nonlinear analysis in here, but there are nonlinear analysis packages. Not every structural application or every type of thing that we can apply to finite element analysis is a linear equation. So what do we mean by that? What's our big fundamental equation? Okay, KD equals F, right? That's a linear equation, right? Our displacements are directly related to our forces. That's a linear equation. That's what a linear analysis means. There are situations, if we keep it really simple, thinking about springs, a steel spring with force applied to it, F equals kx, that's a linear equation. You deal with a rubber spring, a big chunk of rubber, F equals kx does not apply to a rubber spring. And so typically there is some kind of plot of force versus displacement that looks like this. Or something, depending on the type of spring, something else, maybe just not a straight line. Okay, so that's a nonlinear relationship. So if you're going to model that and find an element analysis, you have to use a nonlinear analysis because there is not a straight line relationship between F equals K and X. Okay? So buckling can be solved in a linear way or a nonlinear way. Solidworks is a linear package. It solves things in a linear way. And so they have an algorithm that uses linear calculations to estimate the likelihood of buckling to occur. Okay? All right. When we're worried about buckling, the areas of the model that is important to us are going to be the thinnest areas and the areas that are in compression. There are multiple ways that something could buckle. Just like we did the frequency analysis, we had multiple modes that something could buckle. But in the case of buckling, really it's the first mode is what's going to fail. It's sort of like talking about a chain that has links of different strengths. Okay? There's different places the chain could potentially break, but it's always going to fail at the weakest link. So you get multiple modal outputs, multiple buckling modes can be output, but the most useful one is the first one because that's where it's going to actually fail. And so you can find the weak areas of your model, or you could, if you're designing tank cars that are going to be steam cleaned, you could try to reinforce the car such that if somebody did close it overnight, that it could withstand the vacuum of atmosphere, the atmospheric pressure on the outside of the vacuum on the inside. We could design the tank car to handle that. Obviously, the reality of that is if we did design it for that, then we're designing it for something that maybe would happen only occasionally, but you're going to have to pay the penalty of every car is going to be more expensive because you've designed for that. Okay? Probably a much cheaper way to do that is to put some pressure relief valves in it or something that would allow that vacuum to be released if it was ever inadvertently created. Okay. I think I just talked about this. Pretty much linear versus nonlinear analysis. There is programs that do nonlinear analysis, and we can take advantage of those programs. For example, for Solidworks, if we're interested in what happens when a material yields, we want to do analysis of a guardrail crumpling. Well, there's not a real good way to do that in SolidWorks. We can detect when does it start to fail, but once it starts to fail at its yield strength, we don't have any way in SolidWorks to take that further. Okay? So, but there are programs out there. There are ways to do that with nonlinear analysis. If you ever get into that type of analysis, what I would encourage you is just be aware that software is out there, that type of analysis can be done if you need that type of thing done. Other nonlinear analyses are when displacements are very large, something we haven't talked about probably with, or maybe a reminder back to strength of materials. Those equations that we use are assuming that the displacements are small. Okay, so if I'm looking at the force on the end of a cantilever beam, and I want to know how much does it deflect, the assumption built into the equations is that this deflection is small. And what exactly is small? Well, I don't have a real good definition of that for you, but orders of magnitude smaller than, say, the length of the beam. But if this is 10 inches long and I'm deflecting it 10 inches, that's a large displacement in my equations that I find from in the back of the book, in the 211 book, is probably not going to give me a good answer of what those deflections actually are. Okay? So I'd have to turn to something like a nonlinear FEA analysis to predict what those actual displacements are if I have large displacements. The last thing there for nonlinear analysis is boundary conditions change during the application of loads. Maybe a good example of that would be, what if I have a beam that is bending and there is something sitting down under here just below it? So I apply this force, it bends down and it starts touching this piece down here, and all of a sudden I've changed from a cantilever beam to something that has a simple support over on this side. My boundary conditions have changed in the middle of my analysis. And if that happens, then again, that's not something that we can approach with a linear program. So contact analysis, where bodies deflect such that they come in contact with other bodies, would be an application of a nonlinear analysis package. So just be aware that those exist. The rest of these slides are a quick review of 211. And so I included them here with the assumption that it's been a little while since you calculated buckling loads. So I put them in here for you, but this is totally a review. These were the slides back when I used to teach 211, these were the actual slides I used. I don't know if these are ones that were used by other professors after me. I'm pretty sure I gave them to the others. But with the columns that we did in 211, we're trying to calculate what is the maximum load that it can handle without buckling. We called that the critical column load. The end fixity was important, whether it was pinned or fixed or fixed free. There was a factor for that. And then we calculated what was called the slenderness ratio. And the slenderness ratio was a relationship, the length, the end fixity factor, and the radius of gyration of the cross section. And if you recall back, does anybody remember what the radius gyration is? I forgot. Look to see. I put it on there, right? So it's what is it related to? It's related to the moment of inertia and the cross-sectional area. Okay, the ratio of those two, the square root of those two. Okay, so hypothetically thinking, if I have a really large moment of inertia and a relatively small area, then I'm going to get a large radius of gyration. Conversely, if I have something that's really compact, has a small moment of inertia relative to its cross-sectional area, then I'm going to get a very small radius of gyration. Okay? So the slenderness ratio tells me whether or not I have a long or a short column. And so I calculate my slenderness ratio, and then I calculate my column constant. Column constant is a function of the modulus elasticity and the yield strength of the material. So these two things are material related to determine my column constant. And then I compare the two. And if my slenderness ratio is greater than my column constant, that is a long column, and I'm going to use the Euler equations for beam buckling. And if the slenderness ratio is less than the column constant, that means it's a short column, and I use the J.B. Johnson equations. Those sound somewhat familiar to you? I see a few nodding of heads. So if you did this back in 211. So calculate slenderness ratio, calculate column constant, then decide if you have a long or a short column. This is the Euler equation. The critical load is given by this equation. See, I have modulus elasticity, moment of inertia, and then the equivalent length. So that's factor of the length, the actual length, and the end fixity. And that gives me the critical load that column can handle if it's a long column. So when we're doing these are the hand calculations. I'm giving you all the equations that you need in order to do some hand calculations for the assignment. JB Johnson is for short equations, a little more complicated mathematically, but the same factors play in there, and it also gives us a critical load that a short column can handle. With a short column, we're going to have yielding of the material is going to be more important as opposed to the longer columns are going to, the stability of it is going to be less because they're much longer. All right, so got a blank slide here. I want to do buckling in Solidworks. How am I going to analyze buckling in Solidworks? I've never done it before. How am I going to figure out how to do that? You're sitting there at your computer at 11 o'clock at night. You're not brave enough to text me at 11 o'clock at night to ask how do I do buckling. How are you going to figure out how to start buckling?
When you do your study, you obviously want to click buckling and start that way.
Okay, so that's a really good guess. If you didn't get that far, you're stuck with trying to do a static analysis, and you can't find anything in static analysis of how to do buckling. What would be the next thing?
SolidWorks help.
Okay, SolidWorks help, right? Okay, or even Google it and find somebody's made a YouTube video of how to do buckling in SolidWorks, right? So I'm trying to, maybe prod you a little bit to, you can figure this out on your own. I'm trying to give you a little bit of background, a little bit of understanding, but you should be able to find a tutorial on how to do this. So I would highly encourage you to read the buckling help and SolidWorks help. If you bought the textbook that I recommended, I don't think there's anything on buckling in it. If you want some other references, I'll be happy to share those with you. Okay. But there's a new type of study. The study is very similar to the other types of studies we've done in that you start the study, you give it a name, and then you define, or you probably have already defined the geometry involved. You're going to tell it how is it constrained, does it have fixed connections, and so forth, what kind of loads are applied to it, and then you run the analysis. And the output of the analysis is going to be what SolidWorks calls the buckling load factor. Okay? And this is a screenshot straight out of the SolidWorks help. And you will get buckling load factors for your structure. And it will be a contour plot like you're familiar with. And when you look at it, you will see that if the buckling load factor is greater than 1, then buckling is not predicted. Okay? So if everything on your structure is greater than 1, then buckling is not predicted. If you have buckling load factors that are between 0 and 1, then you have a problem with buckling, and it's going to buckle. Or SolidWorks thinks it's going to buckle anyway. The way you've got it modeled, the math is going to predict that it's going to buckle. So we're looking for, and actually if I would have written this, I would have said buckling, I would have said greater than 1, I would just change this to greater than or equal to 1. Because then we have another column here that says if buckling load factor is equal to 1. Okay, so we could have simplified that a little bit. But buckling is predicted if the buckling load factor is greater than 0 and less than or equal to 1. And then the rest of this table is the opposite of this with negative numbers. So now if the buckling load factor is between 0 and -1, then buckling is predicted if the loads are reversed. And why would I be interested in that?
Well, if it's the pressure thing, I mean, you had a high pressure inside instead of a low pressure.
Okay.
Or if the load's cycled somehow.
Right. It's pretty common to put loads on SolidWorks structures that are actually alternating. And you put it in one direction, but in reality, it might go one direction, then reverse and go the other direction. Okay, so if you have a load that is alternating, and you have buckling load factors that are between 0 and -1, then you still have a problem, because when the load reverses, it's going to create a buckling problem. Okay? So a lot of loads are actually cyclical, where they go positive and negative, and so we'd have to be worried about the negative loads as well. Okay? So, I forgot to print out the assignment. Let's pull up Blackboard real quick. This is assignment 9. Okay, and the first part of assignment 9 is do the buckling analysis for the truss that we've looked at several times. So again, you're not having to recreate geometry. You can use the same geometry you had before, just do a new analysis where we calculate the buckling load factors. Part 2 of that then is a column. So this is more like what we've done. I think I just have 2, yeah. This is more like what we did in 211. The difference here is that this, because it has the holes in it, does not have a standard modulus elastis or a moment of inertia, right? The moment of inertia is smaller where the holes are than where the holes aren't. So can we calculate this using 211 strength of materials equations? Yeah, we can approximate it. We could probably get an upper and lower bounds on the P critical. You use the smallest cross section to calculate the P critical, and use the largest cross section to calculate P critical, and our actual P critical should be somewhere in between. The geometry is here. It's a little hard to see, but I think there's enough information there geometry-wise for you to recreate this. If you can't read it, let me know, and I'll try to enhance it a little bit. But there's dimensions for that given below, and it says we're applying a compressive force of 30,000 newtons on the end piece down the length of this piece. Okay? For the first part of this assignment, to do a hand calculation, you could figure out, you could take individual pieces of this. I don't think you necessarily have to do the entire truss, but you could pick like from G to F. You could do a hand calculation, figure out what if this is, assuming this is in compression, and it's probably not because it's on the opposite side. So you probably want to pick like B to C. That one's going to be in compression. You could figure out what the compressive force is there, and then you could use the Euler or the J.B. Johnson equations to do a hand calculation to compare to Solidworks. Okay? Any questions about that?
When we do these, do we use a mesh or is it a shell? I would think you do a mesh, but
Well, mesh is not a type of,
Well, I mean,
Element.
for buckling, I mean, for some of these previous ones, for the static ones, they had an element type, but for buckling, it's different as far as.
well, but you can use any type of element type.
Okay.
So for the truss there, you've already modeled that as or as
Yeah.
beam elements, so I would leave it as beam elements and model it as beam elements. This one, I think you need to use shell elements. This
Yeah.
is thin, this could be represented easily as two-dimensional flat plates, right?
Yeah.
So I think shell elements would be appropriate for this one,
Okay.
if that's what you're asking.
Yeah.
Yes. Okay? Anything else? Okay. That's what we're working on for 7 and 9 then.